Swayam Prabha. Digital India. Educated India.
We have discussed a lot about the soil characteristics, and we have devised different types of strategies to understand how the origin of soil occurs, how soils get redeposited, and how they are classified based on their redeposition and the transportation agency. Later on we talked about some indices which characterize the soil mass, and they were Atterberg limits. That in short was the interaction of the soil with water, and we wanted to study what really happens when soils come in contact with water. From there on we moved to discuss about the compaction characteristics of soils, and this was the first time when we talked about how the microstructure or the porous structure changes because of the external impact of the loads or the stresses. Then we talked about the seepage characteristics, and then we tried to understand based on the coefficient of permeability how the soils can be characterized. I am sure you must be realizing that all these discussions which we had done until now are valid for characterization of the soil mass. Subsequently, we talked about the stress which develops because of the external loading in the soil mass, and this is where the compressibility comes in picture. That means, when the soil mass is exposed to external loading, how it responds, and this could be a sort of an engineering behavior. So, I am sure the common thread between all these discussions which we had until now is to understand the response of the soil mass to the external stimuli or to the fluids or to the pressures which are being exerted on them. So, in today's lecture I will be discussing about the compressibility characteristics of the soil mass, and what I have written over here is this is compressibility and consolidation, because once we have understood the compressibility characteristics of the soils, we will move on to discuss about the consolidation characteristics of the soils. As the name suggests, the compressibility is the compression undergone by the soil mass, and this is mostly because of the external loading. In the previous lecture we have talked about how the stresses can be computed in the soil mass because of the external loading. Now, if I consider the compression of the soil mass, this is normally we talk about, or we are interested in, the volumetric compression. Now, volumetric compression of the soil mass would depend upon the state of the soil mass, and the type of loading which acts on it. We have already studied the type of the loadings. This could be the point load, this could be the uniformly distributed load, this could be different types of loadings which we have talked about in the previous lecture. Now, as far as the state of the soil mass is concerned, normally we deal with a dry state it could be a partially saturated state, or it could be a completely saturated state. So, when we define the compression characteristics of the soil mass, it becomes important for us to understand soil is in what state, dry state, partially saturated state, or the saturated state. Now, suppose if I consider a surface, this is the ground surface, let us say, and there is some loading which is coming on the top of this. So, normally we say that this is delta sigma. Now, delta sigma is the one because of the construction of this facility over here. Now, if the soil mass happens to be dry, what is going to happen? The compression is going to be due to the expulsion of air. Why? Because air is compressible. Okay, as compared to the soil grains which are incompressible. And so is water also. If I am dealing with the dry soil and if I load the dry soil system, the chances are that the air will being compressible will go out, but the soil grains which are incompressible is not going to be deformed. Alright. However, when I change the scenario, I will be talking about the third case directly, that is when you have the saturated state of the soil. This is because of the expulsion of water, the volumetric deformation is going to occur. Okay, because water is incompressible and it takes time to move out of the pores and there is a time lag. That means this process of expulsion of water from the soil pores is going to be a function of time, and this is mostly because of the fact that hydraulic conductivities of the geomaterials are extremely small. Particularly for the fine grained soils. Alright. So, the situation is like this, that the moment you load the system of soil mass from outside in the form of delta sigma, the amount of some air may expel out and there could be a compression. The major contribution of the compression is going to come because of this process, and hence we say that volumetric deformation of the soil mass is going to take place because of either the expulsion of air, expulsion of water, or the third one could be the compression of or reorientation of soil grains. Alright. So, these are three responsible factors. Now, when I was talking about the particulate nature of the soil, I had this small model that suppose there is a loading P which delegates to sigma, and I had talked about two situations. Suppose this is the soil mass and the lateral sides are unconfined, alright. So, this is the unconfined soil mass. If I keep on increasing the intensity of the load, say from P to Pn, where Pn is greater than Pn minus 1, is greater than Pn minus 2, is greater than P, what is going to happen? If I do not have a confinement, the tendency of the particles would be to first, the whole soil mass will get compressed, and then because there is no confinement, the tendency of the soil mass is to flow out. So, if I restrict Pn to such a limit that Pn itself is less than the yield strength of the soil. Now, we do not write sigma y over here, we will be writing the shear stress. So, suppose if I say the shear stress y, alright. In this case, only the compression is going to take place. Why? Because the shear strength of the soil is higher as compared to the stresses which are getting delegated into it, and hence there is no slippage, there is no rolling over, there is no reorientation of the particles, and hence this is a pure case of the compression. This is what actually we are going to study today, A part. However, if reverse is true, and if I say Pn creates a stress which is greater than the yield strength of the soil, this becomes a shear strength analysis. So, shear strength dominates the mechanism of load transfer. Hope this part is clear to you. So, part number B we are going to do in the second course. This will be dealt with under shear strength theory, and not today. However, the part 1 A will carry on with the discussion on A. That means, we are restricting to a situation where the state of stress in the soil mass because of the external loading is not going to exceed the yield shear strength, alright, and hence the compression only is going to govern the process. Is this part okay? Oh, this is the P, that means the load, and if you compute the stresses along with this will be sigma n greater than sigma n minus 1 to sigma. So, these are the stresses, these are the loads. Below this is the yield strength of the soil, yield shear strength of the soil, alright. So, coming back to the issue, see what we have done until now is, we have defined the compressibility in such a manner that this is the fundamental characteristics of the soils and its engineering property, and it basically tells you about the response of the soil mass to the external loading. A follow up of this would be the consolidation process, which we will be discussing in the subsequent lecture. So, this is how actually the compression has to be defined. Now, what I intend to do in today's discussion is, I will be talking about how to quantify the compressibility characteristics of the soils. So, the question is, how would you obtain the compressibility of the soils? So, that is the determination of compressibility characteristics. of the soil mass. There are two ways. The first method is which is known as a oedometer test. We call it as oedometer test. Find out what is the meaning of the word oed. So, this is a hollow ring of steel, stainless steel, normally 75 mm in diameter and 25 mm in height, and made up of about 0.5 mm thick metal. Now, this is the oedometer ring. Oed is basically a sort of happiness. So, the name is a interesting name. This is what is known as a oedometer ring. Alright. So, this is a stiff stainless steel hollow ring of dimension 75 mm and 25 mm. Sometimes people use 50 mm diameter, and the moment it becomes 50, this will become 20 mm. So, these are the standard things. So, one is by conducting the oedometer test and filling the soil sample in this ring and then applying a normal stress. Alright. So, sigma is the stress which is applied on the soil sample, which is contained in a hollow ring which is made up of steel. Now, steel gives enough stiffness, and hence the radial strains in this sample tend to 0. That means there is no deformation of the steel ring. So, when you apply the load on the soil mass, there is no radial deformation taking place in the system. So, this becomes a opposite case where we had talked about the unconfined. This becomes a confined boundary, and when confined boundary is there, this is what gets simulated with the oedometer ring. When I load it, the only possibility is that the soil grains are going to get compressed. There is not going to be a shear failure. There is not going to be any rolling, and there is slippage along the plates of the fine grained materials. Now, unfortunately, this is not a very realistic situation. Because most of the situations which prevail in the nature or in practice are 3 dimensional. I hope you can realize that this is a 1 dimensional loading and 1 dimensional deformation of the sample. So, that means if I keep my sample like this, so if this is the sample to begin with, the moment I have loaded it, and normally rather than having a point load, what we do is we distribute this load on the surface. So, this is how the P load is acting, which gives a sigma stress. Now, this is not a very realistic situation. So, in order to create a realistic situation, what we can do is we can obtain the compressibility characteristics by doing a triaxial testing. this is 3-dimensional in nature. What we do is we take a cylindrical sample. So, this is the cylindrical sample. You must have noticed here what we call is as the diameter d, and this is the height of the sample h. So, we maintain d by h ratio as 3. Alright. This is what the typical situation is, and I hope you can realize that why d by h is kept as 3, because in the previous lecture when we were talking about the stress which is getting induced into the soil mass, when your dimension of the loaded area is 3 times the height of the sample, all the stress bulbs which are going to get confined into the sample would be 99%. You got this? So, geometrically we force all the pressure bulbs to remain confined in this system, and hence I can assume that the loading is uniform on the sample from top to bottom. Clear? That is the reason. So, when we do triaxial testing, we apply, let us say, sigma 1 over here, sigma 2 over here, and then sigma 3 over here. Normally we maintain sigma 3 equal to sigma 2. So, this also becomes a biaxial testing, but it is in 3 dimension. Then we will be talking about the triaxial tests for obtaining the shear strength characteristics of the soil mass. So, let us again remain confined to odometer test, which is 1-dimensional in nature. Okay. And as I discussed, when you apply this stress over here, so the deformed sample would look like this. This is the deformed sample, and I can say that there is a deformation of, let us say, delta h, and delta h is the reduction in height of the specimen of the soil, because we have taken some small portion of the soil mass, we have fitted in the ring, and then we are trying to find out how the compression characteristics look like. Now, delta h is the compression also. So, rather than writing reduction in better scientific language, this can be replaced with the compression. What is the significance of this? If you have a soil mass, and suppose if I lay a foundation on the top of this, alright. So, this much of this compression of the soil we are going to observe due to external loading, provided the soil is same. So, this soil is same as what you have in the nature. You have taken out some sample over here, filled in the ring. Either I can remold this sample, or I can take rings which I can insert into the soil mass, I can take them out, and this is how we can collect a undisturbed sample, and that sample can be inserted into the loading frame, and I can load it and I can get the deformation. Fine. So, this becomes the odometer testing, which is what we are going to discuss in today's class. So, let me discuss a bit about the 1-dimensional odometer test, or the consolidation test we call it. There are 2 methods of doing the analysis. particularly when we are working with fine grained materials. Like either clays, or you might be having silts, or you might be having clay silts or silty clays, so on. Normally, we do not talk about the compressibility characteristics of the coarse grained materials, because as I said, the grains are incompressible, and hence there is no point in talking about the compressibility of the dry soils, particularly the granular material. So, when we talk about the fine grained soils, in order to simplify things, what we do is we saturate them. How saturation is done? This ring, which is containing the specimen of soil, normally this is placed in on a pad in such a manner that this pad has a groove in it, alright. So, this is what is known as base plate, and this base plate is connected with a drainage tube or the drainage. We call this as a drainage port, and this drainage port can be connected to a water column. Fine. What we do is, in order to spread the load which is coming on the sample, we put it on porous stones. So, we place porous stones in this groove. This is the porous stone, and one similar porous stone is kept on the top of the specimen which is contained in the ring. So, if I show you the ring like this, in which the specimen is contained, so this is the oedometer ring, with a specimen of the soil mass. We will put a porous stone at the top also. So, this is porous stone number 2. Or you can say top and bottom. Alright. On the top of this porous stone comes a loading pad. This is made up of steel, and there is a groove in which I can keep a ball. So, this is the loading cap, and this is the ball which is made up of steel, stainless steel, and this is connected to, entire thing is connected to a load frame. So, this is the loading pattern, or sorry, loading assembly we can call it. So, this is the machine or the loading frame. I can read how much load I have applied, or I can devise a system by which I can apply a certain known amount of the load on the plate. I also attach a dial gauge over here, and this dial gauge gives us the deformation undergone by the specimen when it is loaded. So, dial gauge is DG, is used for obtaining the delta H. Alright. So, dial gauge gives you the readings that after you applied the stress on the sample or the load, how much the deformation the specimen is going on, that is delta H. And I hope you can realize that area of cross section remains constant. Of the specimen remains constant, and hence delta H is also equivalent to delta V, the volume. Now, choice is mine. If I want to do a study on a dry sample, I can do it. You can prepare the sample, you can take dry soil, you can pack it in the odometer ring, and you can apply stressors and you can obtain delta H. I can vary the moisture content of the fine grained materials, and I can fix them in the odometer ring, and I can study the compressibility characteristics. Normally, when we deal with the fine grained soils, as I was saying, to make life easy, we saturate it, we make sure that the sample remains saturated always. So, when we do this test, we open the valve and we allow water to remain always filled up in a container, which is a bath. So, this becomes the water bath, and this remains flooded with, in fact, the water bath should be up to the higher limits of the specimen. So, the water can be maintained up to here. So, sample remains or the specimen remains submerged in water all the time, and hence we are ensuring that we are obtaining the saturated state deformation characteristics, compressibility characteristics of fine grained soils in particular.